So as Dean said, today we're talking about the strategies for designing effective and efficient car park ventilation systems and ultimately eliminating costly, ineffective, and unsightly ducted systems. In this presentation, we have 9 modules in total. We will begin with design goal and code requirement. We will then move to the challenges of traditional ventilation solutions. We'll talk about jet fans and how they work. We'll provide you the latest certification and standards applicable to jet fans and their performance. We'll review optimizing ventilation design. I'll discuss a couple of real-world project analysis for effectiveness and energy efficiencies in the process. We'll start to tie it up with summarizing what we, Buckley and SystemAir Solutions Driven Partnership, can provide you, extend that through our coordinated solutions, and then lastly, I'll give you a 2-minute review of who we are at SystemAir. So with that being said, let's begin. First of all, the code and design you will find within the ASHRAE Handbook HVAC Applications, Chapter 16. In 1998, a study was funded by ASHRAE to do research to determine what the chief factors are for understanding and determining the effective ventilation rate for enclosed and underground parking. And those factors are the acceptable level of contaminants in a parking facility, the number of cars in operation during peak conditions, the length and time of travel and distance within the garage itself, which is also very reliant on the geometry of the garage, and then the emission rate of a typical car under varying conditions, such as a hot start vehicle, warm start vehicle versus a cold start vehicle. And from that study, it was determined that 35 parts per million for up to 1 hour is acceptable. Now, many projects set a design goal of 25 parts per million to be in compliance with an 8-hour exposure. So that gives you more of a frame and a reference of the code requirement and in the background. Looking at International Mechanical Code and ASHRAE Standard 62.1, and this may be redundant to everyone, but we're going to go through it just as a friendly refresher and reminder. Enclosed parking garages in North America, they are required that they introduce a ventilation rate of 3/4 of a CFM 0.75 per square foot of parking deck for the garage was in operation. And that is a continuous ventilation rate while the garage is in ventilation. In 2015, IMC was revised to state that if you tie the ventilation system to a gas controlled, so in other words, creating a demand on controlled ventilation system, if you tie to that, then you can reduce that continuous ventilation rate from 0.75 down to 0.05, provided you maintain the ability to ramp back up to 0.75. Again, implementing the intention here is to create a demand on controlled ventilation system. If we look at International Mechanical Code and where and how it's adopted throughout the United States, because understanding that the Northeast, specifically Boston, is a hub for design work throughout all of the United States and elsewhere. So we want to look in all regions of the US for a bit of a background here. So when we look at International Mechanical Code adoption by state, you see states in blue, yellow, green, and in orange. So as an example, the states that are in blue, they have not yet adopted statewide International Mechanical Code. The states in yellow, they have adopted statewide International Mechanical Code 2015 iteration. The states in green, they have adopted International Mechanical Code 2018 and later to International Mechanical Code 2021. I point that out because per those iterations, they require your gas detection sensors to actually be UL listed. And then you have the states in orange. And the states in orange, they have adopted a pre-2015. They have not adopted that statewide though. They do give a lot of credence and variation to the local authorities having jurisdiction. So if we zoom in just a little bit closer, we look at state of California as an example. The state of California, in addition to International Mechanical Code and their local California Mechanical Code, they also have adopted standards that they find within their building energy efficiency standards. I point this out just to be totally aware that if you're designing projects outside of the typical area that you're accustomed to, there may be varying standards in play. One of those varying standards then would be NFPA, National Fire Protection Association 88A. Now, in 2023, it was amended. Prior to 2023, you see what's on the left. And this is how they addressed the requirement for mechanical ventilation in an enclosed or underground parking. Basically, it was very simple. Move 1 CFM per square foot. That was it. That's how they addressed it. Now, in 2023, they amended that because there was some awareness that was in a burgeoning of awareness driven by companies such as yourself and companies such as Buckley and SystemAir, that may not be totally effective. So in 2023, you see they went from 6.3.4 to now include 6.3.5 all the way down to 6.3.5.6. I couldn't say that again if I had to. Now, what I want to do is draw your attention quickly to what's highlighted in red here, because that's really the meat and potatoes behind this, although I do recommend you become fully familiar with the 2023 version of 88A. We point out here that 6.3.5 now says that mixing fans, and for this application we're talking about jet fans, shall be installed in parking structures where any of the following conditions apply. So let's look at the very first two, because they have a big impact. One, that says that where the shortest distance between any point of the supply air to the closest point of the exhaust air is greater than 300 feet, you must include mixing fans. Also, number two, and they're talking about open parking structures. So if you have a parking structure that is partially enclosed, or you would consider it enclosed, but meets the minimum requirements by typical standards to not require mechanical ventilation prior to the 2023 iteration, it now says that even though you meet those minimum standards, if the opposing openings, fresh air, if those opposing openings are greater than 300 feet or 91 meters, you also must now include booster fans, mixing fans, we call them jet fans, in this application. So I'm not going to go through the entire amendment or every point. I'm just pointing this out for you to be aware as you move forward with design. Now let's talk about the challenges of traditional solutions. Here you see in front of you some typical applications, sweeping system, ducted systems. This has been the go-to design for many, many, many years, and it, quite honestly, is accepted by code plan checking and permitting across the country. But there's a challenge here, and what you're going to find that I say a lot through this presentation is that the code requirements are simple. That is true, but effective and efficient ventilation is also very challenging. Again, I want to point out here, it's easy to move the right volume of air, but the challenge is to how to effectively mix, dilute, and evacuate those contaminants. So when we look at the problem of traditional sweeping systems and traditional ducted systems, I use this to illustrate. You see, we have a 3D model on the left, and we have that model in plan view undergoing CFD analysis on the right. And the process of CFD analysis at this stage is to understand airflow and their patterns. And you can see here, you have green arrows that represent the passive airway through the rampways, and you have the red arrows that indicate the mechanical extraction points by exhaust fans. So you have the air that's coming in, it's under its own momentum, even though it's under influence by the mechanical extraction fan, the mechanical exhaust fans, it's under its own momentum due to that influence. So that air takes a long, slow sweeping path as it comes in and moves over towards the exhaust points. Part of the challenge we have with the traditional systems is they do not induce much airflow. They have a limited effective range. Ducting versus jet fans is an expensive undertaking, and they result in dead air zones in hotspots. Now we can typify this here. We can see it here while it's close to being taking place under CFD analysis. But once we introduce contaminants into the space, it really starts to take a life on its own. It really jumps out and gives you that visual. Now, we introduce contaminants through CFD analysis based on the four factors: cold start versus warm start, percentage of vehicles that would be used within the space, time and distance of travel into the garage and through the garage. That's how we determine and quantify the volume of the parts per million of carbon monoxide into the space. Now you see here, this particular garage is under full ventilation rate. It is moving 0.75 CFM. So this particular garage would fall within compliance of the code and standard. But by looking at the carbon monoxide at full ventilation rate, you see there's areas of the garage that's certainly not healthy. 300, 500, in the center of the garage, 1,500 parts per million. That is because even though we've introduced the correct volume of air to be code compliant, this space is not getting the maximum benefit of that ventilation rate that's introduced. That's part of the challenge. That's part of the issue, the challenge that we have with traditional sweeping and ducted systems. Understanding this to be the issue for a long time, engineers have addressed this. And they said, well, what we can do is we can either put in ducted systems to replace the traditional sweeping system. And if we don't use ducted systems, we can put in square inline fans or axial man cooler fans like you see installed there. But here's the problem with this, and this is a challenge in looking to that as being the solution. These fans are not designed for this application. They induce very little air, have a very limited effective range. Typically what we found looking from design to design all across the country and even into Canada, that because these fans are not designed for this application, there's no quantifiable means to understand or predict how well they will perform in this application. So what we typically find is engineers either put in way too many of these fans or put in far too too few of these fans. Part of the issue here is at that point in time, since these fans are not designed for this application, an engineer from design is relegated to put these fans where they will fit, not necessarily where they're required. So with that being the case, we look at the jet fan to be the solution. To understand the jet fans, we're going to talk about how they work. So first of all, a jet fan its performance is not like any other type of fan. There's no static pressure to be concerned with, no fan curves. Any static pressure is internal to the fan. These are unducted systems. And they operate off the impulse principle. And what the impulse principle is the result of a relatively high rate of discharge combined with a relatively nominally small area of discharge that results in air being discharged from a fan and being thrusted or pushed out into a local environment, wherein it collides with the air in front of it, creates friction, and that friction induces air. So in other words, a jet fan, through the impulse principle, by means of induction, would put air into motion many times greater than its AMCA rated airflow. That being the case, we have 4 key performance factors when we look at the performance of a jet fan. Now, I want to be very clear here. These 4 performance factors are all equally important. One has no priority over the other. So we'll start with induction, and that's pretty simple. The induction factor is the volume of air that's put into motion, which is many times greater than its AMCA rated airflow that is actually passing through the fan. Axial jet fans have an induction factor. Centrifugal jet fans have an induction factor. Now we're going to look at thrust. For thrust, it's measured in newtons. Now, some manufacturers measure their thrust in pound force, not a problem. We specify or publish our data and measure it in newtons. Now, a newton is basically just a SI unit of measure that considers a 1 kilogram volume of air and the pound force that it takes to move that volume of air from a distance to a distance where it reaches its terminal velocity. So pound force and newtons are totally translatable. And when you reach the terminal velocity, based on that measurement of pound force required to move it, when you reach the terminal velocity, and for this case, the terminal velocity for jet fans in underground parking application is 1 meter per second, or 196 feet per minute, we'll just say it's 200 feet per minute. When it reaches that distance, that's what's called its throw. So that's the throw length. So that's the distance at which the volume of air is thrown to where it reaches that terminal velocity. Now, we use 1 meter per second or 200 feet per minute because that is considered in underground parking, especially in moving contaminants, that is considered the optimum speed, velocity, to effectively mix, dilute, and move contaminants. Anything slower is not totally effective. It will eventually get there, but it's not totally effective in quickly diluting contaminants. And then lastly, you have airflow. Airflow is simple what it is. It's the AMCA rated airflow that is being put through that fan while that fan is in operation. But these are all four equally important. So with this, I will show you an actual CFD analysis, a visual model of a jet fan in operation. So you can see we have the jet fan here on the left. This is in the first section of the model. And the model space is 100 meters long, 20 meters wide, 3 meters high, open on both ends. We'll do this one more time in case you want to see that again. This is an axial jet fan in operation. You see the discharge of air and the additional volume of air that's placed into forward motion by the discharge. So now we will look at a centrifugal jet fan in operation. Now you notice the difference here is a centrifugal jet fan. It is a little slower moving. It doesn't have the high airflow CFM, the same as a high thrust axial jet fan, but it puts into motion a considerably larger area of induced volume of air. Now let's talk about the correct certification and the standards which apply to jet fans, because this has been a question and it's come up. Hey, which is the correct certification to specify? Well, the correct certification is the AMCA standard 250. And that is because the AMCA standard 250 directly prescribes the test methodology specific to jet fans in the application of enclosed and underground parking. That standard is only applicable to jet fans. Now you see, prior to AMCA reintroducing or updating their AMCA 250 to actually be an AMCA 250-22, previous to that, manufacturers could test their jet fans to AMCA 210. And some manufacturers still test to AMCA 210. But there are fallacies in that, it being that if you're familiar with AMCA 210, it provides and prescribes a variety, I think 14 to 16 different test configurations. It could be unducted, it could be ducted, it could be with accessories in the airstream, it could be inlet only, discharge only. There's a multitude of test configurations, all of which none have anything to do with the actual jet fan in an underground parking application. So that is why AMCA moved forward, and following their revision to the 2018 Certified Ratings Program, by introducing AMCA 250, they said that they will no longer certify jet fans under AMCA 210. And you see here, this is part of the test configuration that is used to measure, one, the total sound power level of the jet fan in its operation, not inlet only, not discharge only, the overall sound power level, and mechanically qualifying the test methodology to determine the actual thrust produced by that fan. So you can see there is a big difference between the previous certifications, AMCA 210 and AMCA 250. If you're specifying jet fans, you should be specifying jet fans to be in compliance with AMCA 250. From that now, we're going to talk about optimizing ventilation design. And here we're actually going to start to give you the discrete differences in the performance and the characteristics of the volume of air that's put into motion by an axial jet fan and a centrifugal jet fan. Because an axial jet fan provides a jet stream of air to push contaminants towards an exhaust location, whereas a centrifugal jet fan is still a high thrust, but it's also high induction. That provides a very wide enveloping airflow discharge to quickly dilute contaminants on their way to extraction. So I have four modules here we're going to talk about. Contour plot at X direction, contour plot velocity magnitude at 5 feet off of the garage floor, contour plot velocity magnitude inside view, and then we're going to illustrate the area of dilution. To set the table for this module here, I'm going to set the basis data, which is going to be consistent for the next 3 slides, including this one here. Basis data, we're going to use an axial jet fan that you see on the left at the top, and that's 6,085 CFM. It has a thrust, high thrust, 51.5 newtons. It throws to a terminal velocity of 126 feet. It has an induction factor of 8, a very good induction factor. So that says that 6,085 CFM, when in operation, puts into motion the equivalent of 49,754 CFM. Now, over here to the right, the basis data we're using is for a centrifugal. It's a high thrust, high induction centrifugal jet fan. Now, right away, you see it's 3,517 CFM. Now, if you were to look strictly at these two models right now, airflow versus airflow, your question would be, well, shouldn't I just go with the higher airflow? Not unless you look at all 4 key performance factors, which is very specific to jet fans. So when we look at the centrifugal at 3,517 CFM, 51 newtons of thrust, it throws to the terminal velocity of 154 feet. Based off the impulse principle, combining the relatively high rate of discharge with the nominally small discharge area, you see we have an induction factor of 22.9. So that fan, being high induction, when in operation, in motion at 3,500 CFM, actually puts into a forward motion of a little over 80,000 CFM. So you start to see the separating of the pack here. Now, I want to draw your attention to the CFD modeling down below. The left is the axial, on the right is the centrifugal. At the first cross section of modeling through the tunnel here, you see once the discharge of the axial jet fan pushes downstream through the tunnel, you start to see some dark blue colors develop. What we've done here is we're illustrating that the dark blue colors, that's a negative velocity. In other words, that's air that's no longer moving forward. It's actually starting to swirl and even possibly move backwards. And that was evident in the CFD model video that we showed earlier for the axial fan. Whereas over here to the right, where you see the centrifugal fan, through the first cross section is the location of the centrifugal fan. As it discharges its airflow, we still have a few small areas of negative velocity, but they're very minimal, and they're actually pushed out wide to the left and the right of the airflow discharge. And actually, that does not occur until very late in its throw, and it doesn't create a huge negative impact to its airflow the same way as you would have with the axial. For expediency here, I'm going to skip this and move right to the slide that probably will give us the better illustration. And that's this right here. This is the contour plot velocity magnitude at side view. Here's what we're illustrating here. If we look at the top image and compare that to the bottom image, the top image through CFD analysis, we're illustrating the airflow pattern of the axial jet fan versus the centrifugal. Now the top image, what we've done is, you see here for both scenarios, we're setting the minimum velocity for the minimum speed to be 1 meter per second. Because remember, anything slower than that is not fully effective in diluting the contaminants and moving the contaminants. And we've also overlaid our 5-foot line of gas detection. Now, most manufacturers will tell you to place your gas detection sensors anywhere from 3 to 6 feet off the floor of the garage. And that's not by happenstance. But if we look at this, you see over here with the axial fan, yes, there is slow moving air that will be drawn up into that jet stream, but for the most part, you're seeing the air does not get down and breach that 5-foot line of gas detection until somewhere around 49 feet or so, and it tops out somewhere around 65 feet. So it has very minimal impact down through that point of line of gas detection. Whereas beneath that, with the centrifugal fan, you see, again, there will be slower moving air drawn up and induced into the stream or the airflow pattern. But once it breaches that 5-foot line of gas detection, it gets all the way down, fully enveloping from the top of the garage to the deck of the garage, all the way through its length of throw. It's creating a much larger area of dilution. Now, you may ask yourself, why is that important? Well, this is why it's important. When we look at, and again, I want to point out, it's not by happenstance that a gas detection manufacturer will tell you to place a sensor 3 to 6 feet. Now, that is our typical pedestrian breathing zone, but we also need to look at the characteristics of the contaminants itself. So when we look at the specific gravity of the contaminants, such as carbon monoxide, nitric oxide, nitrogen dioxide, and nitrous oxide, they are different. If we look at them in relationship to air and the specific gravity of air, if we look at that as being typical 1.0 at normal pressure and temperature, air being 1.0, your carbon monoxide is 0.967. Whereas if you were to look at your nitrogen dioxide, that's 1.44. So carbon monoxide is slightly lighter. Nitrogen dioxide is considerably heavier. What happens there then is your nitrogen dioxide will sink down to the lower part of the garage, and your carbon monoxide, which is the most prevalent contaminant based off the vehicle types that we see today in parking garages, that stays somewhat aloft. Now, the only thing that, here are the things that influence gases: temperature, pressure, and air movement. So if we don't have the air movement to greatly influence these contaminants, you may have an issue where you have a high stagnant area of concentrations. So that's why it's important to have a fan discharge profile similar to a centrifugal jet fan that gets all the way down through the length of its throw to get rid of the carbon monoxide, dilute the carbon monoxide and the contaminants in the process. Lastly here, this also gives you a better representation as well. What we're doing is we're looking at the contour plot where we reach the terminal velocity. So you have the cross section on the axial jet fan on the left where it reaches its terminal velocity. At this point in time, it's, again, terminal velocity is the same, 1 meter per second or 200 feet per minute. And we introduce a 5-foot line of gas detection, which is now represented by the black line. You see here at that point in time, we've set the maximum velocity to be 196 feet per minute, or the 1 meter per second that we need to effectively dilute, mix, and control contaminants. At that section, at the end of that throw, we're not even breaching the 5-foot line of gas detection. Matter of fact, to get close to breaching that 5-foot line of gas detection, we need to be down at least less than 100 feet per second, considerably less. Whereas over here, if we contrast that with the centrifugal configuration and its high induction and discharge pattern in this scenario, you see at that same 5-foot line of gas detection, at the terminal velocity distance, setting the same parameters at the slowest speed to be the maximum speed 196 feet per minute, we see we have a larger area of dilution, considerably larger area of dilution, because that is part of the characteristics of the volume of the air that's put into motion by a centrifugal jet fan as opposed to an axial jet fan. And so when we look at the challenges and the advantages of one versus the other, because there are real type applications and good applications for axial jet fans, and obviously there are very good applications. Probably the majority of underground parking garages benefit greatly from a centrifugal jet fan, but we want to look at both of them here. So you see 3 images. Top left is an axial jet fan installed on a project. The center is a centrifugal jet fan installed on a project, and the top right is a centrifugal jet fan installed tight to ceiling on a project. You see, to get full maximum benefit from an axial jet fan, it needs to be installed fully beneath structure, like you see in the image, and you also see in the graphic down beneath that. Now, you have to be full of obstructions from the inlet all the way through the discharge. Now, you don't have that challenge. If we look at the same type of garage ceiling webbing structure in the center image as we do on the left, you can see here with a centrifugal jet fan, which relies on its inlet air through the bottom of the fan and discharging out to the side of the jet fan, you see you have a much greater variety of solutions that you can implement in placing these jet fans. So as an example, in this complicated structure here, the only portion of the centrifugal jet fan that needs to be fully beneath structure, even as close as we are in this application, is just the discharge of the fan. So for perspective, I want to point out to you the discharge of that fan is 3 inches. It's actually 2 7/8, but we call it 3 inches. So you have much more greater ability and design varieties at your disposal rather than being limited to the challenges that are provided by the larger size with the axial jet fan. And as illustrated by the jet fan on the right, they can be installed tight to the ceiling. So we've covered 1 through 5. Now let's look at project analysis and energy study. So I'm going to talk to you about 2 projects. One is Carnegie Mellon University in Pittsburgh, and the other one is Terramina Family Apartments in San Diego. And in these in the analysis I'm going to show you, we're going to talk about the effectiveness of controlling carbon monoxide and the energy efficiencies of controlling carbon monoxide, comparing a jet fan system versus traditional sweeping and a jet fan system versus traditional ducting. So the first project here is CMU in Pittsburgh. Now you see the image, it represents the 3D model for the parking garage. You see the placement of the jet fans. The blue arrows call out the green entrances for either rampways or for louvered openings. So there's passive air inlet. And the red arrow down at the bottom represents the exhaust fan location. Now see, the concept here from the original engineering design was to use the supply fans at the top to push air down the garage, and then use the exhaust fan at the bottom to pick up that momentum and pull it through the bottom left of the garage, while having fresh air coming through the rampways and the louvered openings. This is a mechanical passive system. What we're going to do here is we're going to create what's called a steady state analysis. So with the garage ventilation being totally turned off, based on the parameters outlined by ASHRAE, we're going to introduce carbon monoxide uniformly throughout the garage. And then what we're going to do is we're going to go into what's called a transient state, where we turn on the ventilation system and we review the time it takes to cleanse that garage from carbon monoxide from the high level established you see here of 672 parts per million down to the design goal of 25 parts per million. And we're going to do that comparison for the traditional sweeping system alone and the traditional sweeping system optimized and supplemented by the jet fans. So you can see here in scenario 1, it took 39 minutes for the traditional sweeping system to cleanse the garage to get it from 672 parts per million down to 25. And in fact, if we look at the first 3 minutes of operation, it reduced carbon monoxide by less than 1.5%. The scenario over here to the right is the traditional sweeping system, but now optimized by jet fans to better mix and dilute and control the contaminants. You see it only took 8.3 minutes. And in fact, looking at that same 3-minute period, more than 80% of the carbon dioxide was reduced. So this is a time-lapse video to show you and better illustrate what we're talking about. At the top up here, you see we have the inlet air pushing in. It hits an obstruction. It starts to turn and make its momentum around the obstacle. Down here at the bottom left, where we have the exhaust, right here you can see we have a great deal of short cycling. Because of the location of the louvers and because of the location of the inlet ramp, you have a lot of short cycling. Now, at this point in time, the engineer couldn't help this because he was very limited in the space above him because of the green space required. He was very limited. This was the only place that he could put exhaust air, and at the top was the only place he could put the inlet air. So at this point in time, considering all this short cycling, we're moving the correct volume of air. By code and standard, this meets the requirement of moving 0.75 CFM continuously, but the space is not getting the maximum benefit of the ventilation rate introduced. Now, with jet fans in operation, a couple different things you see here. One, you have a much better uniform cleansing of the garage. You have a much better reduction of carbon monoxide. And even down here at the bottom left, because we use the jet fans and the supplier of the jet fans to control the flow distribution throughout the garage, we can actually capture this air at the bottom left corner where we were having all that short cycling and eliminate that short cycling. So what's taking place here is the garage space is actually getting full benefit of the ventilation rate that's been introduced, which is required by code. So let's talk about the energy efficiencies, because we've already illustrated the effectiveness. Well, when we look at the energy efficiencies, the supply and exhaust fans accounted for 36 horsepower, or a total of 32.5 kilowatts. Now, the runtime, it took 39 minutes to cleanse that garage. That's actually 0.65 hour at the total kilowatts it results in a total energy runtime of 21.28 kilowatt hours. All right. Now, down here at the bottom, the scenario where we've introduced jet fans. Now, you may say, John, how can you become energy efficient by introducing more horsepower? Well, we're introducing the right kind of horsepower in the right kind of fan to do the right kind of job. So we went from 36 horsepower to 52 horsepower, or a total kW of 47.3. But the runtime to reduce the carbon monoxide and cleanse that garage is considerably reduced. 0.15 or, 0.14 or 6.62 kilowatt hours. Now, this is a nearly 70% reduction of energy. So it's not only effective in controlling the carbon monoxide, it's energy efficient. And this is the intent and the design goal behind International Mechanical Code, implementing the ability to reduce the maximum ventilation rate, the continuous maximum ventilation rate, from 0.75 down to 0.05 if you tie to gas detection, because you're creating a demand on control ventilation system. We're letting the jet fans take the brunt of the operation in diluting the carbon monoxide, so the supply and exhaust fans can run more efficiently, more continuously, and more frequently at that reduced minimum rate. If we look at payback, we look at cost of energy, cents per kilowatt hour, and this is based off of the U.S. Energy Information Administration report from September 2023. It's almost a year old, but still very relevant. And we look at the cost of energy. The project was located in Pittsburgh. Now, we made some assumptions. And some of the assumptions that the study is based on is operating 15 hours a day, having peak operation hours from 6:30 to 8:30 a.m., 11:30 to 1:30 p.m., and from 4 o'clock to 6 o'clock p.m. Now, these are typical peak activity hours for garages. Some may seem more, some may seem less. This is typical. And in this, you see the sweep ventilation system alone, at the total kilowatt hours of 1,423, was a cost of $7,739. Now, when we supplement that ventilation system with jet fans, and we look at the total kilowatt hours reducing from 1,423 to 306.6, that operating cost drops from $7,700 down to $2,400. This is a payback. It's about 6.8 years. And that is a payback that is actually very substantial. So moving on, we're also now going to look at Taormina Family Apartments. This is a project in San Diego, California. And here again, we're also going to talk about the effectiveness of controlling carbon monoxide in a ducted, a system where we're comparing a jet fan versus ducted. And then we're going to talk about the energy efficiencies of going from a ducted system to a jet fan system. So on this particular project, the engineer designed in the beginning what he wanted to do. He had a challenge, and what he wanted to do was he designed a ducted system, kind of like you see here, the duct all in red. But he had a goal to remove the ducted system that's highlighted by the blue arrows. He had a spatial limitation. He wanted some more overhead clearance, and he said, I need to get rid of this ductwork. So he looked at his options. And his options, let's go back here for a second. His options are to either go with a total sweeping shaft system or to go with a total ducted system. And this is what he was coming up with here. He said if he looks at the shaft sweep system alone, there's a negative impact created to the project. So again, through CFD analysis, we introduced carbon monoxide, and we introduced carbon monoxide uniformly based off the criteria found in ASHRAE. You can see that under maximum ventilation, we're moving 0.75 CFM. Under maximum ventilation, this garage could expect areas that are 500 up to 1,124 parts per million of parts per million of carbon monoxide. So the sweeping system, shaft alone, is not an option. So his next option was a ducted exhaust system. And then obviously SystemAir presented the third option, which is a jet fan ventilation system. So we're looking at the differences between the two. When we look at the vector velocity of magnitudes of the ducted system, you can see you have still a lot of short cycling of the air that is being influenced coming in directly into the garage, because it's under its own momentum that's being created by the influence of the ductwork itself. So it wants to come in and take its own path. Whereas over here, you look at the jet fan system, the jet fans can use that and control that flow distribution to capture that air and push it where we know we need it to go. So from that standpoint, you see there's a big difference in the velocity of the air that we're working with. But let's also then look at the contour plus velocity magnitude at the duct height and at the jet fan height. And what you see here is there's a more uniform distribution at the consistent velocity. Okay, you have high velocities entering the rampway of the garage, and then it kind of slows down drastically, where you get an average speed of about 31 feet per minute. Now over here, you have, again, a more uniform distribution, because we're capturing that air and we're distributing the flow throughout the garage where we know we need it to go. And there you have an average speed at the jet fan height of about 111 feet per minute. But let's look at the difference in the resulting carbon monoxide levels. So here on the left, you see the ducted system. It did reduce the carbon monoxide from the 1124 parts per million down to 314 parts per million in two sections there. In a couple areas, we're still exceeding 200 parts per million. Now, that's at maximum ventilation rate. All right, so without understanding CFD analysis, this meets the intention of the code that's in place, because it's a distributed duct system that is no further than 50 feet apart, and it moves the correct volume of air. But it's not healthy. It's not a healthy indoor environment by any means. But over here on the right, you see the jet fan ventilation system. It reduced the carbon monoxide from the 1124 parts per million down to 155 parts per million. That is within the 200 parts per million standard that is allowable for a 15-minute exposure. Now, when we do this, we want to also then look at, I'll give you a visual illustration here. This that you're seeing at this point in time, this is the ducted system in operation. And again, you see, because of the inlet air passively through the rampways, it creates its own momentum because of the influence of the ducted system. So the air comes in and it wants to take its own sweeping path throughout the garage. And part of the challenge here is it's not being evenly distributed. We think it would be with ductwork, but it's not. It's not being evenly distributed to gain full benefit of the ventilation rate that's introduced. And we counter that here with the jet fan system. The jet fan system, as you can see now, because we strategically placed jet fans to capture that inlet air, we're no longer placing it or relying on it to be under its own momentum due to the influence of the shaft air. We are actually influencing that air to capture it and to push it where we know it needs to go to be more uniform dilution throughout the entire garage space. That's a big difference. But now we can start to look here. Let's summarize this here with effectiveness. We started with 1124 parts per million based on the space with the shaft alone. Now the shaft, aided by ducting system, reduced the carbon monoxide down to 314, which is 72% of the carbon monoxide. Okay, it reduced it by 72%. Over here with the jet fan, starting with the same 1124, it reduced by 86%. So it reduced it from 1124 down to 155 parts per million. But if we look at the comparison between the ducted system and the jet fan system reduced an additional 50% carbon monoxide, greater than what the ducted system did. So what we have here is jet fans provide a greater reduction of carbon monoxide when comparing to ducted systems. And from an energy efficiency standpoint, again, the ducted system took 67.5 minutes to cleanse that garage down to the design goal. that 314 carbon monoxide down to the design goal 35 parts per million. That took 16.7 kilowatt hours, whereas the jet fans took 27 minutes to reduce the 1124 parts per million down to the design goal of 35 parts per million. It took 27 minutes to totally cleanse that garage. At that point in time, that was 6.71 kilowatt hours, or a 59% reduction in energy. So the takeaway here is that jet fans cleanse the space and reduces contaminants almost 2.5 times quicker when compared to the ducted system. In summarizing that, it's easy to see that jet fan dilution systems, whether you're comparing to a traditional shafted system or whether you're comparing that to a traditional ducted system, does a much thorough job in a more timely, energy efficient manner of cleansing and removing the carbon monoxide. So to add a little bit to what Dean said earlier, what do we offer? As a solutions-driven partnership between Buckley and SystemAir, we offer design and layout assistance. If given the opportunity, we review the project, identify the correct supply shaft locations, and the team at Buckley identifies the correct supply and exhaust fans. We identify the correct jet fans and the correct jet fan location. Buckley also can provide the gas detection system, and we can provide the CFD analysis to validate. So in case you were wondering from one of the previous example, what I wanted to show you, where it was challenging on this sweep system alone, 300, 500, 1500 parts per million, SystemAir designed a jet fan system that reduced the carbon monoxide level at maximum ventilation rate to achieving down to 65 parts per million throughout the entire garage, with the exception of this one small little boot hill, which was 99 parts per million. So that was extremely effective, and I kind of figured you were probably wondering. But now let's talk a little bit about the coordinated solutions that we provide. Again, as Dean said earlier, and what I just said a moment ago, it's an overall solutions-driven package. Okay, it's a systems solutions driven. Code compliant fans brought to you by Buckley, control and monitoring system brought to you by Buckley, and the jet fan induction systems brought to you by SystemAir. That's how you create a healthy indoor parking environment. So at SystemAir, we design, engineer, and manufacture axial jet fans, centrifugal jet fans of 50 newtons thrust and 12 newtons of thrust, and they are all AMCA 250 certified. One thing I want to point out about axial is SystemAir has two models of axial, and we recently introduced our AJRQ model. Now, one of the biggest objections to an axial jet fan, just call it what it is, they're loud, inherently loud. By design, they're inherently loud, even with integrated silencers. But at SystemAir, we were able to redesign two particular models that we offered, and while improving the overall airflow and the induced volume of air, going from 3,600 and 4,900 CFM to 4,100 and almost 6,000 CFM. We were able to do that while reducing the overall sound levels of 81 and 79 dBA down to 74 and 75 dBA, all while being AMCA 250 certified. Now, we also offer the IV50 EC, which is a very low profile 10.25 inch jet fan, fully speed controllable, very energy efficient. This is the fan that produces a 3,517 CFM, AMCA 250 certified to 73 dBA at 3 meters. Very quiet in its operation. And then we engineer and manufacture the IV Smart EC. This is the industry's most widely designed with and specified jet fan. It's just under 6 inches in profile. It's an EC-driven fan. It's a 1,482 CFM, 11 newtons of thrust, an induction factor of 28.6. So that 1,482 CFM puts into motion an equivalent of 42,459 CFM and throws to a terminal velocity of 129 feet per minute. It's also available in an option to include Modbus communication to be an integrated part of your building management system. So all being told, SystemAir, Buckley, our solutions-driven partnership, can provide to you one coordinated solution to include supply and exhaust fan to meet the code compliance requirements, the gas detection and control system to operate an intelligent system, and the jet fans to optimize the ventilation system to ensure that the ventilation rate being introduced by code requirement provides the full benefit throughout the garage space, all while being energy efficient. So with that being said, I'm going to give you 2 minutes of who we are at SystemAir, because you may not be familiar with us. SystemAir, first of all, we are a global resource, global development, but we provide local solutions. Our last fiscal year sales was $1.2 billion. We have approximately 6,600 associates, and we manufacture in over 20 factories. And you see them kind of located here throughout the world. So we have global resource, global development, local solutions. When we look at what we are as a company, is we provide what we like to say is better air. And we provide better air everywhere by engineering, by design, by manufacturing. So we can provide better air for a data center. We can provide better air for healthcare facilities. We can provide better air for infrastructure, transport, and industrial. We can provide better air for commercial applications. We can provide better air in residential applications, in education, and in hospitality and in entertainment. So we help you design better air everywhere. But we bring that local. So our jet fans that we've just been talking about today, which are all AMCA 250 certified, are all manufactured in Lenexa, Kansas. If you're not familiar with that, it's a suburb of Kansas City. You might have some appreciation for this. I do. That's also home of the Kansas City Chiefs. But I just want to say that Kansas City Chiefs, got to get that in here at one time. I'm joking. But that being aside, we manufacture all of our jet fans out of 150,000 square foot manufacturing facility. It's also home to 2 of our AMCA certified laboratories. But rounding out our strength of engineering and manufacturing here in US and Canada for North American region, we have manufacturing and engineering for our thermodynamics, heating and cooling equipment in Tillsonburg, Ontario, Canada, which is not far into Canada from Detroit. And we have engineering and manufacturing for our injury recovery equipment in Bactouche, New Brunswick, Canada. Now, Bactouche, New Brunswick, Canada, it's not the end of the world. It's a very beautiful part of the country. I always recommend everyone, if you have the opportunity or the need to go there, please do so. But it is almost like a planes, trains, and automobiles to get there. It's not easy to get there, but once you're there, you certainly appreciate it. That being said, that brings us to the end of the presentation, brought to you by the team at Buckley & Associates and SystemAir. You can find more information at systemair.com US or systemair.com for our global sites. And as always, you can find additional information by reaching out to Dean and the team at buckleyonline.com.